fundamental theorem of algebra. If P is a polynomial with complex coefficients and the degree of P is greater than 0, then there exists some R in the complex field such that P of R is 0. And so this says that any non-constant polynomial has a root that is possibly complex. So if we allow us to, if we extend our field to the field of complex numbers, then we can solve any polynomial, any non-constant polynomial, and get that it's some complex number. Now, of course, it could be, you know, maybe a complex number where the imaginary part isn't possible, but it's, you know, possibly a complex number, possibly imaginary. Okay, so I'll give you a quote-unquote proof by Louisville's theorem. Louisville's theorem says that any bounded entire function on the complex plane is constant. And an entire function is one that's basically looks like a polynomial with possibly infinite degree. And so 1 over P of X is a bounded entire function on the complex plane. And well, if since this is bounded entire, then it must be a constant. But we said that it wasn't a constant. So therefore, it's that contradicts the fact that P of X was not 0 in the complex plane. Okay, so the maximum number of roots. If, let's call it I, if I is an integral domain, you know, such as the set of integers, then every polynomial with integer coefficients has at most degree P number of roots, counting multiplicity, in this integral domain I. Well, let's see what could go wrong. Okay, so what if it's not an integral domain? So suppose I want to solve x cubed. And I want to solve that in z sub 8. Okay, so actually, let me insert something here. Even though we sort of said it before, but maybe I should give you sort of a recall. So recall. Z, well, let's recall modulo. So A mod B is the remainder of A divided by. So, for example, 5 mod 2 is equal to 1, since 5 divided by 2 is equal to 2 with a remainder of 1. Remainder is 1. We don't really care about the quotient. We just care about the remainder part. Okay, so Z mod n is equal to, well, it's a set of all integers, and I'll just write it this way. 0, 1, 2, up to n minus 1, where we have the following, where if I add 2 elements or multiply, so if I have 2 elements here, then A plus B in Zn where I've defined this as being A plus n. So defined by, so this addition here is defined by A plus B mod n. And A times B is defined by A times B modulo n. Okay, so maybe I'll give a little bit more explanation of this. Okay. Move this over. Okay, so for example, since I'm giving an example of 8 here, maybe I'll do a Z8, for example. In Z8, let's take 2 elements in Z8, 5 plus 4. Is equal to 9, but I want to do this mod 8. And so if I take 9, so I just look at the remainder. And so 5 plus 4 is equal to 1. And let's see, 2 times 3 mod 8 is equal to 6. 6 divided by 8. Well, the remainder will just be 0. The quotient will just be 0 with the remainder of 6. So that'll be 6. Let's do 5 times 4. Well, what's 5 times 4? 5 times 4, 5 times 4 is 20. But then let's divide this by 8. So 20 divided by 8 is 2 with a remainder of 4. And so I just write down the remainder, 4. So all I'm doing here is just writing down the remainders. You could even do, if you wanted, like an exponent, 2 cubed. Let's do 2 cubed. Mod 8. Well, 2 cubed is 8. 8 divided by 8 is just 1 with no remainder. Okay. So, well, actually, I just saw something there. Okay. So that's sort of weird, that somehow you bring it to a power and it just gives you, 0. 3 cubed. Well, let's see what that is. Mod 8. That's going to be 27. 27 divided by 8 is going to be, 24, so that's a 3. So the answer is 3, because I'm just looking at the remainder part. Five squared is 25. 25 divided by 8 is 3 with a remainder of 1. And so 25 squared mod 8 is just 1. With that practice, let me do the following example. Solve x cubed equals 0 in Z8. Z8 is a sort of a bad sort of object. Okay, so note A is equal to B in Z8 if A mod 8 is equal to B mod 8. In other words, the remainder of A divided by 8 is equal to the remainder of B divided by 8. We will show that x cubed equaling 8 has roots x equals 0, x equals 2, x equals 4, and x equals 6. It has 4 roots. And so in Z8, but it's a cubic, which, if you recall, a cubic has at most 3 roots. So Z8 is actually not an integral domain. That's, if it were, something like the integers, then I could do it. And the reason is because the 8 is not prime. If 8 were prime, if I did Z5, Z19, everything would work nicely. But Z8 is not good. Okay, so let's check. Well, 0 cubed is certainly 0, because 0 cubed is 0. How about check x equal 2? Well, 2 cubed is 8. 8 divided by 8 is 1 with the remainder of 0. So 2 cubed is 0 in Z8. Let's do x equaling 4. Well, 4 cubed is 64. 64 divided by 8 is just 8 with the remainder 0. These are all powers of 8. So 4 cubed is 0 in Z8. Let's check 6. And so 6 cubed is 216. But if you divide 216 divided by 8, you get 27 with no remainder. And so 6 cubed is 0 in Z8. So there are 4 roots to a polynomial of degree 3. And so there are 4 roots to this cubic polynomial, but that does not contradict my previous statement because Z8 is not an integral domain. Another example. Oh, shows Z8 is not an integral domain. So let's do that. Well, an integral domain is a set. It's an algebraic thing, object, where the zero factor property holds, meaning that it's supposed to be that if A times B is 0, then either A is 0 or B is 0. But let's look at Z8. 2 times 4 is 8. But, so therefore, 2 times 4 is 0 in Z8, but 9 is 0. So the zero factor property does not hold for Z8, meaning it's not an integral domain. Okay, so let's look at the number of real roots. So now let's, instead of looking in general at an integral domain or things that aren't integral domains, let's look at the real numbers. If f is a polynomial with real coefficients, then the number of roots in f is less than or equal to the degree of f. Many times it's strictly less than. And so I don't know how many roots there are, but at least I know what the maximum possible number of roots. Then the maximum number of possible real roots is the degree of the polynomial. In C, we know how many roots there are. So the number of roots theorem. Let P be a polynomial with complex coefficients, and suppose that this is not so I'm going to take the polynomials with complex coefficients, take away just the complex numbers, meaning I'm taking away any polynomial that only takes on one value. So I'm looking at non-constant polynomials with complex coefficients. Then there are exactly the same number of roots as the degree of the polynomial, so long as we count multiplicities. And so in the field of complex numbers, they're exactly n complex roots, so long as you count multiplicities. Polynomial factorization, and let's do this on the field of complex numbers. Let P of x be a polynomial with complex coefficients, and let the degree of this polynomial be greater than 0, so we don't want it to be a constant polynomial. Then P of x is equal to some number, a sub n, times the product from j equaling 1 to n of x minus r sub j. In other words, it has the form an times x minus r1 times x minus r2 times x minus r3 dot 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 x minus rn. That's what this symbol here means. Where n is the degree of your polynomial, and r sub j's, that'll actually be the roots of your polynomial, are complex numbers, and a sub n is the leading order coefficient of your polynomial p. The factorization theorem. Let p be a polynomial with coefficients in some field, f. Then the degree, so 1, if the degree of f is 0, then f is a unit. It is neither irreducible nor can it be factored. It's a, 23. You can't really factor 23 as a polynomial, or let's say 24. The number 24 cannot be factored as the polynomial just consisting of as a polynomial. You can't write it as the product of two polynomials of degree less than the degree of the original polynomial. So it can't be factored, but we say it's also not irreducible because it's a number. It's not a polynomial. It's because it's not a polynomial. If the degree of f, oh, now I called it f. Probably because I don't know why. So I called it f. I guess I didn't see it from one page to the other. I changed it. Okay, so if the degree of f is equal to 1, then f is irreducible. It's of the form x minus 3 or something. It's x minus r. So it's an irreducible polynomial. If you had something like 2x minus 4, you could write it as 2 times x minus 4, x minus 2, but the 2 is a unit. So you're just taking out a unit, so you're not really changing it. So it's not, you can't factor it as a polynomial. Even though I would want you to factor out constants, it's not actually incorrect if you don't factor out the constants. Because it's, if I'm asking you to do factorization, rather than just degree of the polynomial is either 2 or 3, then f is irreducible if only if f has no roots. And so irreducible in degree 2 and 3, irreducibility is the same as factoring. And so irreducibility is the same as looking at roots to your polynomial. So factoring and finding roots of your polynomial are the same if you're looking at degree 2 and 3, but not in general. If the degree of f is greater than or equal to 2, then f being irreducible implies that f has no roots in the field f. In other words, if f of r is 0 for r being in the field, then f factors in the polynomials having coefficients in f. Because this means that by the factor theorem, x minus r is a factor of f. Okay, so let's do on page 518, problem number 12. Determine how many roots each equation has. X to the 40 equaling 1. So in this case, there'll be 40 roots in the complex field. So if I'm only talking about the complex field, then I know that there are 40 roots. Okay. Now, if I'm looking at something else, say the real numbers, there may be less than 40 roots. So in this case, if I'm looking at, and maybe I should sort of say that, because it'll depend on what they're asking you. So let me answer this in more than one way. There are 40 roots in C. So that's a true statement. But there are only 2 roots in R. So if I'm looking at x to the 40, well, actually, there are only 2 solutions if I'm only looking at real numbers. 1 and plus, so plus and minus 1. So if I look in the real numbers, 1 works, and so does minus 1. But no other real number works, right? If you take, like a half and raise it to the power of 40, you're never going to get 1. The only time you can get, if you take a number and you raise it to the power of 40, well, it's got to be plus or minus 1, and nothing else works. So if I'm only talking about complex numbers, I know how many roots there are. If I'm talking about some other field or integral domain, then, well, finding the number of roots could be a little bit more difficult. I don't just look at the power. But for complex numbers, I do. Let me do problem number 14. Negative 32 x to the 111 minus x to the 5 equaling 1. So in this case, there'll be 111 roots in the complex field. There'll be less roots if I look at some other field. Problem number 18. Determine how many linear factors and the polynomial has. And so the number of zeros. Recall that zeros are the same as number of roots. The number of zeros which is the same as the number of roots. Well, let's again even though zeros are usually when I ask for a zero of a root, a zero of a function, usually they're real. So number of zeros, let's first do this on C. So let's do the complex zeros. So the complex zeros, well, that's a number of roots, which in this case is 40. Okay. If I look at the number of zeros on R, so let's do this for the real field. So this is the number of roots on R. Is, well, let's see. So let's try to figure out what that is. That's x to the 40 plus x to the 39 equaling 0. So this is x to the 39 times x plus 1 equaling 0. Well, let's try to count this up. Well, there's only one root here, x equaling -1. It has multiplicity 1. Here, the root will be 0, but it has multiplicity 39. So therefore, the number of zeros on R is equal to 40. Because there are 39 plus 1, counting multiplicity, zeros. So it's a total of 40 zeros. So I'm counting, if counting multiplicity. Okay, so now let's figure out the number of linear factors. On R or C, because we notice that they're actually both the same. So in this case, we're able to factor it into 1 plus 39, 40 factors. Okay, so now let's look at automorphisms. These will become important. Well, they were found to be important by Galois in solving of polynomials or determining when polynomials have solutions and how they can be determined. Unfortunately, his algorithm is quite unyielding. So it's done in a finite amount of time, and people can do it on a computer, but by hand it's not nearly so efficient to calculate. So we usually do other things, but these are still important because they will help you to save time by doing things involving this. So first, let P be a polynomial with rational coefficients. Then, if A plus rad B is a root of your polynomial, with A being a rational number and B being a rational number, such that A plus radical B is irrational, then the A minus rad B is also root. So what you notice is that roots come in conjugate pairs. If the solution to your polynomial was of the form 2 plus the square root of 3, then 2 minus the square root of 3 is also a solution. So notice that this automorphism, changing the sign of the second object, well, it really doesn't do anything to the rational numbers. Okay. But if this quantity here is not in the rational numbers, then its conjugate will still be a root of your polynomial. Suppose P is a polynomial with real coefficients. Then A plus BI being a root of your polynomial, with A being real, B being real, and A plus BI being irrational, meaning that I'm assuming B is not 0. And so it actually is irrational. It's not a rational. I'm sorry. It's a non-real number. I was saying it is this. Notice that these statements are the same. You start in some field, but you assume that this root here is not in your field, then you do the same thing, but you subtract it. So if A plus BI is a root to your polynomial, then A minus BI is also a root to your polynomial. So we have that roots come in complex conjugate pairs. So if 2 plus 3i is a root to your polynomial, and the polynomial only has real coefficients, you have to have this complex conjugation cannot change what's happening to your coefficients of your polynomial. So if you had had complex coefficients would change the values of your coefficients, and you do not want to change the value of your coefficients. So this complex conjugation, this automorphism, has to fix your coefficient field. Okay. So write a second degree polynomial equation with real coefficients and the given root. So let's use this conjugate pairs theorem. We have real coefficients, so we're using this second statement saying that if I have real coefficients, then roots come in conjugate pairs. And so if negative 3i, I need more space, is a root to your polynomial, then so is positive 3i. And so I have that both 3i and negative 3i are roots to my polynomial. And so my polynomial I'm going to look at the minimal polynomial, has a form x minus 3i and x plus 3i. So let's see if I can multiply this out to get a polynomial with real coefficients. And so this is the difference of squares minus I squared is negative 1, and so negative 9. And so my polynomial is just x squared plus 9. So you notice that negative 3i is indeed a solution, a root to this polynomial. And so this is my minimal polynomial. For negative 3i. It's a polynomial of least degree that has minus 3i as a root. Okay, let's do the next problem. I want to write a fourth degree polynomial equation with real coefficients and the given roots. So again, we're going to do the same thing as before. If I is a root, well then so is plus or minus I. And if 1 minus I is a root, then so is 1 plus or minus I. So we have to have the complex conjugate of 1 minus I is 1 plus I. So both 1 minus I and 1 plus I are roots. And so these are roots of my polynomial. Or rots if you forget the other O. So roots of your polynomial. So let's look at the minimal polynomial. So let's do x minus I, so that's the plus I, and then the x plus I. And let's do x minus 1 minus I for the x plus 1 plus I, and x minus 1 plus I for the 1 minus I root. So this, well, x minus I times x plus I, that's the difference of squares. And so it's x minus I squared. Let me write this as x minus 1 minus I, okay, times x minus 1 plus I squared is negative 1. And so this just becomes I squared, x squared plus 1. Let's multiply this out. So again, this is a difference of squares. So it's x minus 1 squared minus I squared, which is plus 1. Multiply this out. So this polynomial is equal to x squared plus 1. By the special product formula, this is just x squared minus 2x plus 1 plus my other 1. And so P of x is equal to x squared plus 1, x squared minus 2x plus 2. And so let's multiply this out. So this is going to be, and maybe I'll write it this way, multiply everything by x squared and then by 1. So this is equal to x to the 4 cube plus 2x squared plus x squared minus 2x. Simplify this. So this is x to the 4 minus 2x cubed. Let's combine the 2x squared and the x squared to get 3x squared minus 2x plus 2. And so that is my minimal polynomial, my polynomial of degree 4 with the roots, what was it, I and 1 minus I. Okay, let's do another example. And so write a second degree equation with the given double root. Oh, so this is going to be very similar to what we did previously, I guess 2 problems ago. And so just recall that if 2i is a root, the root to your real polynomial. Oh, of course, this is going to be asking for, so this is equal to, so plus or minus 2i will be roots to your polynomial. Double root. Oh, this is supposed to be a double root? Okay, sorry. So if this is a double root, then that means that it's not an automorphism. So it may not, the coefficients of this polynomial may be complex. So yeah, I'm sorry, it's asking for a double root. So if it's a double root, then both 2i and 2i, they're both roots to the polynomial. And so this will equal, well, x squared minus another 2ix gives me a 4ix plus 4i squared. And so my polynomial will have the form x squared minus 4ix minus 4. The coefficients are not necessarily real. Some of the coefficients here are complex. Okay. So 2i and 2i are roots. Okay, so now let's look at Descartes' rule of signs. So René Descartes, 16. So you've heard of Descartes before when we were looking at Cartesian coordinates. Let P of x, let P be a polynomial with real coefficients. So please note that sometimes I write in, I keep switching in between the two, whichever I want to write it, as P of x or R bracket x. So sometimes I write it as P, sometimes I write it P of x. So let P be a polynomial with real coefficients. Then P of x mod 2 will equal the number of sign changes in the coefficients for P of x. And this will be greater than or equal to the number of positive roots of P of x. The number of negative roots of P of x, mod 2, is the number of sign changes in the coefficients for P of negative x, which is greater than or equal to the number of negative roots of P of x. Oh, good. I was going to say that, but it's written down here. So note, Descartes' rule of sign still leaves uncertainty for the number of real roots to P. An exact test will be given by Sturm's theorem, but let's first do some examples before I give you other things. So notice that we'll just say, well, maybe, you know, there are 2, 4, 8, 12 roots, you know. I won't be able to say there's exactly 4 positive roots. I'll say, well, maybe there's 0, there's 2, there's 4 positive roots. You know, maybe there's 1, 3, 5 negative roots, but I won't be able to nail it down to how many exactly roots, positive or negative roots are, unless the number of sign changes to 0, in which case I can say, oh, there's no positive roots, or there's no negative roots. So if the number of sign changes is greater than or equal to 2, then there will be some uncertainty with exactly how many positive roots there are, exactly how many negative roots there are. Because this only tells you, well, up to evenness and oddness, how many roots there are. So there's an even number of roots, there's an odd number of roots, but at least from the ability before to tell how many real roots there are, we can at least, in that case, say that there are even number of roots, but no more than the degree of the polynomial. There's an odd number of roots, but no more than the degree of the polynomial. So there's quite a bit of uncertainty. The amount of uncertainty is unfortunately more than is ever helpful for you to actually determine, for this to be a useful technique when actually solving polynomials. So it almost never helps other than the case that the number sign changes is either 0, 1. If the number sign changes 0, 1, then this is a helpful theorem. Otherwise, it is not specific enough to really be helpful in determining roots. Actually, even if it's 1, it's not that helpful. If it's 0, it's helpful. And so if the number sign changes to 0, then it's helpful. Other than that, it's really not helpful at all. Okay, so on page 519, use Descartes' rule of sign to find the number of possible positive, negative, and non-real roots of each equation. So what you'll find is there'll be a little bit of uncertainty when I do this. Okay, so first off, let's look at positive real roots. So I'm going to look at the sign changes for plus 5x squared. Oh, by the way, if there are any terms that are missing, like there was no 5x squared here, I put a 0x squared. And then I can arbitrarily pick the sign so that it won't change. Okay, so now let's figure out the number sign changes. So I start with the plus, I keep a plus, but then I have one sign change here. And then I have a minus, but now I go to plus. And so I have that there are two sign changes. Okay. So it's two sign changes. This is a cubic. So there can't be more than 3 roots. So this says that there are either, well, an even number of roots, so either 0 or 2 or 4 or 6 or 8, but I can't be more than 3, so just 0 or 2 positive real roots. Well, maybe I should have called this P of X, just to give some notation. So let's call this P of positive X. Okay. So now let's look at the negative real roots. Okay. Let me add another page here. And so let's replace X by negative X. And so I have here 3 negative X cubed plus 5 negative X squared minus 4 negative X plus 3. So p of negative x is equal to, that's a negative 3x cubed. That's a positive 5x squared. That's a positive 4x. And that's a positive 3. So in this case, I go from negative to positive, but positive, positive, positive. So I only have one sign change. Okay. So I wrote it that way. So there's one sign change. Well, one is good. So either there are, well, there's one. So there's, that says that there's one negative root. So that's good at least. That gives me a definite number. So now, well, it said either there were, so there's one negative root. So one negative real root. There are either 0 or 2 positive roots. So let's first do the 0. 0 positive real root. Or let's, and this is a cubic, so I have to come out with 3 roots. So if there are 1 real root, then there must be 2 complex roots. Oh, and let's see, oh, and this is a real. So there are 2 complex conjugate roots. So 2 non-real complex conjugate. Well, actually, I don't have to squeeze it in so much because I'll never make it. And so 1 negative real root. No, 0 positive real roots. And 2 non-real complex conjugate. Pairs, roots. So that's one possible. So one negative real root, no positive real roots, 2 complex conjugate pair, 2 complex root that come in complex conjugate pairs. Now, lastly, 1 negative real root and 2 positive real roots and no complex roots. Yeah. Need a little bit of room. And no complex roots. Non-real roots. 0 non-real. Okay. Don't freeze. So 0 non-real. Oh, come on. 0 non-real roots. Oh, I already had a 0 there. And 0 non-real roots. And that's your answer. Okay. So there are two possibilities. One negative, no positive, 2 complex conjugate pair roots, or 1 negative, 2 positive, no non-real roots, no complex roots. Let me do problem number 46. So it's the same sort of thing. First, let's look at negative x to the 9, negative x to the 7. Okay. X to the 5, 3, 1. Let's rid of x, 8. Doesn't really matter if I factor out the minus. Let's factor out the minus. X, x8, x6, x4, x2, plus 1. So I can factor out this. Notice that this first term says that there is a 0, that 0 is a root. Okay. And now let's look at the other parts. And so let's look at x to the 8, 6, 4, 2, and 1. Okay, so now let's look at the positive real roots. Well, if I look here, x8, 0, it doesn't really matter. I'll keep it as the same sign. x6, 5, 4, 3, 2, 1. If I look here, there are no sign changes. And so there are no positive real roots, which is good. Since I know that the number of real roots, positive roots, has to be less than or equal to the number of sign changes, which is 0. Oh, it just moved. Okay, good. So there are 0 positive real roots. Oh, come on. Positive real roots. Let's look at the negative real roots. Notice that the zeros didn't make any difference. So I'm not going to write them for the negatives because it'll probably make it just too big. Negative real roots. So P of minus x to the 8, 6, 4, 2, 1. Same polynomial, x8, 6, 4, 2. So again, there are no sign changes. And so no sign changes. And so there are no, did I write 0 or no? 0, negative. Real roots. So this actually gives you something. Okay, so the zeros actually say something good. So I now know exactly how many roots there are. So there are 0 positive roots, negative real roots. Okay. Real roots. There is 1 root equaling 0. There are no positive real roots. And so then the other roots, all but one of them, are complex. So there are 8 non-real roots, and they're all given in 4 pairs. So 4 complex conjugate pairs. So 4 complex conjugate pairs. So we at least know, so in this case, this is one of the cases where I can actually give you a definite answer. And so, good, I can give you a definite answer here. Okay, so now I guess I'll talk about a modification of Descartes' rule of sign. And so with this modification of Descartes' rule of sign, we can actually tell how many roots there are in a particular interval on the real line. So we can look in some interval on the real line. I could look from negative infinity to 0 and say how many roots are there. They'll tell me the number of negative roots. Look at the interval from 0 to infinity. Tell me how many roots are in that interval. So how many positive roots there are. Or I could look at some other intervals and still tell how many roots there are in each of those. First off, the derivation of a polynomial. So let p of x be some polynomial, a sub k, x to the k, for k equal the sum for k equaling 0 to n. And so let's let this be a polynomial with coefficients that are in subfield f in the indeterminate x. Then define p prime, the derivation of p, as the sum from k equaling 1 to n of k times a sub k x to the k minus 1. So we will define the Sturm sequence, p sub 0 of x, p sub 1 of x, p sub 2 of x, dot, 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 p sub k of x, for the polynomial p of x with real coefficients. So I'm just going to look at real coefficients as, so it's the same sort of case for Descartes' rule of sign. And so the Sturm sequence is, well, p sub 0 of x is just defined as your original polynomial, p of x. P sub 1 of x is just defined as, well, the derivation of at x. And then dot, 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 we're going to say p sub I of x is equal to minus the remainder of p sub I minus 2 of x divided by p sub I minus 1 of x. The sequence stops at p sub I minus 1 of x whenever we find that p sub I of x is 0. So eventually we'll come to a stop. That's a sort of the stopping criteria, is that we stop when we all of a sudden we find that this remainder is 0. So once we find the remainder is 0, we're done. Basically, a polynomial of degree n will stop after n terms in the sequence, more or less. Assume that p of x has no repeated roots. For p of x, for if p of x had a repeated root, then we would replace p of x by p of x over the greatest common divisor of p of x divided by p prime of x. Okay. So if it turned out we had a repeated root, we could have done this. So we'll just assume that it doesn't have a repeated root. Next, if p of x has integer coefficients, then the Sturm sequence p sub I of x can be made to be polynomials with integer coefficients if we replace p sub I of x by the following: negative remainder of the absolute value of the leading order coefficient of p sub I minus 1 of x to the power degree of p sub I minus 1, p sub I minus 2, minus the degree of p sub I minus 1 plus 1. All times, so that gives you some number, times basically so that this won't involve a fraction. P sub I minus 2 of x divided by P sub I minus 1 of x. So this will eliminate fractions. However, the coefficients might become quite large. Okay. The sign change function. Let sigma x sub 0 denote the number of sign changes of the Sturm sequence for P sub x when x is equal to x sub 0. Okay, so now the Sturm's theorem. Let P sub x be a polynomial with real coefficients, and suppose P is not equal to 0, then the number of distinct real roots on the half open and half closed intervals from A to B, where we're including the endpoint B, not counting multiplicity, is the number of sign changes, sigma of A, minus sigma of B. So you just are taking the difference of the number of sign changes at for the Sturm sequence at A minus the number of sign changes for the Sturm sequence at B. So let's do an example. Let P of x equal x cubed. So we're going to do it for cubic. Cubic will be kind of big, but x cubed plus x squared minus x minus 2. So we'll probably have at least probably 4 terms in the Sturm sequence. Determine the Sturm sequence for this polynomial. Okay, so let's do that. To locate roots of this polynomial. Okay. Yes. Oh, here it is. Sorry about that. Okay, so let's do this. So I have P of x equals x cubed plus x squared minus x minus 2. Okay. So let's take the polynomial P prime of x equaling so that derivation is just 3x squared plus 2x minus 1. So that was the definition, using the definition of the derivation. Okay. So from this, I get that P0 of x is equal to the x cubed plus x squared minus x minus 2. And the P sub 1 of x is equal to 3x squared plus 2x minus 1. Okay, so now I have that P sub I, and maybe I should write this down, is equal of, maybe I will write it down. I'll write it down, the leading order coefficient absolute value, the leading order coefficient of, in this case, oh, here it is right here. Well, this is it right here. So I'm going to write this down. Oh, I'm going to do it in general. So maybe I'll have to just, if I want to write that in general. Oops. Okay, so let's do this. Insert another page. So, p sub 2 is equal to minus the remainder of the leading order coefficient of, again, p sub 1, which is 3. The coefficient, and of course, I'll just write down 3, I guess, to the power of the degree of the p sub 0. And so the degree of p sub 0 is 3 minus the degree of p sub 1, which will be 2, plus 1. And so this is just going to be 3 squared times p sub 0 divided by p sub 1 Okay. So I have that p sub 2 of x is equal to minus the remainder of, again, 3 minus 2 is 1, plus 1 is 2. 3 squared is 9. So let's multiply each of these by 9. Over 3x squared plus 2x minus 1. Okay, so let's do this. So let's divide this. Actually, let me write this first. 3x squared plus 2x minus 1. Let's divide 9x cubed plus 9x squared minus 9x minus 18. Okay. 3x cubed divided by 3x squared is 3x. Let's multiply that out. So I'll get a 9x cubed plus 6x squared minus 3x. Okay, so that would be a plus 6x squared. And I'm subtracting. So 9x squared, 9x cubes cancel. 9x squared minus 6x squared is 3x squared. Minus 9x minus a negative 3x becomes a plus 3x. So 3x minus 9x is minus 6x minus 18. So let's divide 3x squared divided by 3x squared is just 1. So far, notice integer, all this, these are now done with all integer coefficients. And so let's multiply by 1. So I get 3x squared plus 2x minus 1. I subtract. The 3x squares cancel. Negative 6x minus 2x is minus 8x. Minus 18 minus a negative 1 is the same as 1 minus 18 minus 17. Okay, so the remainder, so p sub 2 of x, is the remainder, which is minus 8x minus 17, but I want to change the sign. So this becomes 8x plus 17. Okay, good. And so now let's figure out p sub 3. Okay, so let's look at this. So it says find the leading order coefficient. The leading order coefficient is 8 to the power of well, these are it's gonna be 2 again, but let's do this. And so because we're always doing the degree of the polynomial, and so it would be 2 minus the degree of the polynomial before, which was polynomial degree 1. So 2 minus 1 plus 1. So 2 minus 1 is 1, plus 1 is 2. So squared. Oops. The remainder minus the remainder. Sorry. Minus the remainder of 8 times, well, 8 squared. It's a squared. 8 squared. Sorry about that, because of the same reasoning here. It's going to become a squared of the 1 2 before divided by the one before. And so the 1 2 before was this guy. The 3, that was the first one, which was this 3x squared plus 2x minus 1. So the 3x squared plus 2x minus 1 divided by the previous one, 8x plus 17, which is good. So notice that means that these are going to help you not to have any sort of fractions in it. Because certainly if you didn't multiply by 8, you have here a 3, and so you're going to get a fraction. Now this is a degree 2, so you have to do one more. So you probably have to multiply by another power of 8, possibly, to make that. Okay, so let's do this. So p sub 3. By the way, p sub 4 is going to be 0, but oh wait, no, p sub 4 is going to be a constant, and so this is going to be no, it'll be 0. So minus the remainder of 64 times 3, 192, 64. Okay, come on. Okay, 8 squared is 64. Okay, times 3 x squared. Plus 64 times 2, 128x, minus 64 over 8x plus 17. Okay, so let's do this. I could use synthetic division, but I guess I'll keep going with long division. And so this is 8x plus 17. Yeah, actually, if you start, well, there's a way to actually do these divisions a little faster using what's called Chinese remainder theorem. But let's just keep doing this. Okay. So 192 divided by 8 is 24x. Okay, so that's 24x. So let's multiply everything by 24x. So I get 192 x squared plus 408 x. So let's subtract. The 192x squares cancel. So I get 408 128x minus 408, which is a negative 280x. Drop down to 64. And so divide that by 8. So I get 35. So let's multiply that. So I get a negative 280x. Oh, come on. Minus 595. Subtract. And so the negative 280x's cancel. Negative 64 minus a negative 595, which is the same as 595 minus 64, which is 531. Okay. And so I get that p sub 3 of x is equal to 531. Now, of course, so notice that I'm going to now divide a polynomial of degree 1 by a polynomial of degree 0. And so my remainder is just going to be a polynomial, well, 0. So I could do that. Well, maybe I'll show you that. So let's try to do p sub 4. Let's go minus the remainder. So what you'll notice is that this was actually the last term in my Sturm sequence. But let's do this. Oops. And so let's do the leading order coefficient. Well, there's only one thing there. So the leading order coefficient of 1 before 531. Oh, this is going to be a huge number. To the power, well, again, it's going to be degree of the polynomial 2 before, which was degree 1 minus degree 0 plus 1. So 1 minus 0 plus 1 is just 2 over the previous polynomial, which was 8x plus 17 over the 531. Well, I can do this. I can cancel these. So the remainder of the division of something divided by 1, there is no remainder, so this is just going to be 0. So the remainder is 0. So the quotient is the 8x plus 17, 31 there, but it doesn't really matter. The 531 times 8x plus 17 divided by 1. Well, dividing by 1 means you're just going to get this quantity as your quotient plus no remainder. And so p sub 4 is 0, meaning that I should have stopped. Okay, so now I've got to collect these. P sub 0 is the original, and p sub 1, oh here, wait, I just got it. So p sub 0 was this. So here is the sequence. So p sub 0 was that. P sub 1 was this. P sub 2 we just got here. And then P3 was the 531. Then P3 was the 531. Notice degree 3210. And that's usually the way it goes, is that usually you keep going down by 1 degree. Unless something horrible happens, usually that's because you have a multiple root, in which case you should have done something else at the beginning to make sure it doesn't have a double root or a multiple root. Okay, so, okay, good. So now, let's say that I want to determine the number of sign changes once I have the Sturm sequence. Let me just see what I was asking, by the way. Oh, this is the Sturm sequence, and locate the roots of this polynomial. Okay, so let's try to locate the roots of this polynomial. Okay, so actually, I'll help by looking at, oh, here it is. Okay, so let's see if I can see this polynomial along with, here it is. This is a calculator. Aha, so I'll just clear this. Clear this. Okay, so here I can put it over here. Okay, so let's put in some, clear that. For the polynomial, I have here x cubed. So let's put an x here into the power 3. Actually, maybe I'll want to make it look nicer. So I'll put here an x and then go to math, and the third one down is cubed, plus x squared. So here's an x squared minus x minus 2. Okay. Now let's do the next one, which is 3x squared. So 3x squared plus 2x minus 1. And then let's go to the next first one in the sequence, 8 plus 17. Go to the next one, which is 531. Well, not that that really matters. That the fourth one is always going to be positive. Okay, so notice that. Okay, so first, let's look at the number sign changes. Let's first go at negative infinity. Okay, so at negative, if something's very large, like negative 50, this is certainly going to be a negative number. And so so I really actually only have to look at the leading order coefficient, the leading order term here. So if I plug in a negative 50 or a negative 1,000, this will certainly be a negative number. Okay, so this will be negative. This will be positive. If I put in like a negative 1,000 or something, if I just put in like negative 50 here, that's going to be negative. I need to get control back of the screen. I got to remember what I was doing. So negative, positive, negative, positive. So the number of sign changes at negative infinity was equal to 1, 2, 3. So there was 1, 2, 3 sign changes. Let's look at, oh, I don't know, negative 2. Or even, let's go for, yeah, negative 2. So let's go back to here, and I'll go to, let's just see if I have the form. Auto. Okay, good. I'll ask. Okay, so the dependent, that'll be auto. Okay, so let's do this table. I want to do it at negative 2, so I'll plug in negative 2. Gives me a negative, positive, so it's a negative 4, positive 7, so negative, positive, negative, positive. It may not have changed. Let's go back to this guy, scroll over some more. That's a positive, 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 positive. Oh, it did change, positive, positive. So there's one root between, okay, so one sign change. So there's one sign change, okay. Let's do it at 0. I can probably figure that out myself at 0. So if I look here, there'll be a negative, negative, positive, positive. There's one sign change. There's no roots. Okay. Let's look at, let's go up to 2 again. Let's insert another. So let's do it at, let's say 2. I don't know, is there going to be root at 1, possibly. Okay, so let's do 2 still. At 2, let's see what happens. So I'll go back. Plug in, let's say positive 2. Taking a while for it to think. Okay, I'm still so far behind. Okay, 2. So it is positive, 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 positive. They're all positives. Okay, so it's a whole bunch of positives. No sign changes. So there's a root between 0 and 2. Okay. And let's see. Is there going to be anything else? There possibly might not be any more. These are all positives. And infinity, these are all positive. Because if I take large numbers, this will be a positive, this will be positive, that'll be positive, that'll be positive. So there are no roots above 2, and there's 1 between. So there are, so 3 minus 1 is 2. So there are roots between negative infinity and negative 2. There is 1 root between I should actually go to negative 3 here just to see what else is happening. So let's actually, so seeing that there are 2 roots, let's see what happens at negative 3. Actually, maybe I'll move this down a little bit so I can put in some more values there. So let's see what happens at negative 3. Possibly even in negative 4. Okay, so negative 3, see what happened there. So let's look at negative 3. Negative 3. Negative, positive, negative, positive, negative, positive, negative, positive. Okay. No, I said it wrong. Oh, this is still, let's see. I was looking at that. Shoot, negative, positive, negative, positive. Yes, negative, positive, negative, positive. I almost looked at the wrong thing. Negative, positive, negative, positive. Oh, so there are no roots there. There are 2 roots between, no, there's 1 root. There's 2 roots between negative 3 and negative 2. Really? Okay. There, 1, 1, 2, 3. Yeah. So that means there are no roots between that are less than negative 3. Okay. There is 2 roots. Okay. Let's look at 2.5 then. Let's just look at 2.5, negative 2.5. Let's see what happens there. Negative 2.5. Negative, positive. Negative, positive, negative, positive, negative, positive. Ooh, that means there's no roots there. There are two roots really close to negative 2. That's 1, 2, 3. Yeah, there are two roots between negative 2 and negative 2.5. Really? Let me just check negative 2 again. Does that really happen at negative 2? Let me just check to see if I miscounted at negative 2. Let's just check. I can't believe there's that many. I did 0.2, negative 2. Okay, so minus plus, 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 minus plus plus plus. Oh, I did minus, no, minus plus plus plus. That's 1. Yes, it is. Okay, so this is kind of weird, but that's life. Okay, so saying that means there are no roots, no real roots between negative infinity and negative 3. Okay. Okay, give me control back so I can write this conclusion here. So there are no real roots between negative infinity and negative 2.5. Yeah, and negative 2.5, negative 5/2. I'm assuming that that's not a root, but I'm sure it's not. Yeah, that's not a root. Okay. There are, so that's between, so there are two roots, two real roots in the interval negative 5/2 to negative 2. So almost all located there. Um, there is, it changes again at between 0 and 2. There is one real root between, what was that? Those 2. No real roots. Maybe let's do the no real roots between negative 2 and 0. So I'm splitting up the line into a whole bunch of pieces out. In each of those pieces, how many real roots there are. There are one real root between 0 and 2. And no real roots greater than 2. Did I give the integer bounds? Okay. And then no real roots. Greater than 2. Okay, so I've split it up into several pieces. So with this theorem, we're able to give pretty good bounds on what's happening. Okay. Okay, good. Oh, some integer bounds. Okay. I should have done it after this. Okay, so let me I got 5 minutes. Okay, let me actually do this in a second after I've done the other one. Otherwise, oh, I see. So some integer bounds for this could be, well, yeah, let's first tell you about this, and then I'll do it. Okay, so let's do. Let me cut this for a second, and then I'll do the other one. Let's cut it. Okay, let's move this other one up. So let me give you some bounds using synthetic division.
Professor, I have a question.
Yes, question.
The problem you just worked out right now, will it be
Yes.
doing it on the test?
Will it be on the test? Not really, no. Because the actual techniques, these are just bound. See, these bounds, any of these bounds that they give you, not really as efficient as some of the other techniques I'll be giving you. So the Descartes rule of sign and Sturm's theorem gives you a little bit, but not a lot. All of these bounds theorems, they're more work usually than what the other techniques are. These would be after you have exhausted everything else, you use these techniques. You don't really use these techniques at the beginning. It's sort of like the default of what could happen when you are completely clueless of other things. So I myself, do I ever use the bounds to help me? In reality, the answer is no. I don't use these. Why don't I use these? They're too much work. There's too much work, enough bang for the buck. There's not enough benefit as compared to all of the all the pain and all the calculations that you actually have to perform to get to it. So I actually don't use these bounds because they are usually not so helpful, but Sturm's is actually helpful. All the other bounds actually don't really help you at all. That sort of deflates the balloon, but in reality, that's what's happening. Okay, so let me give you these bounds on these roots. So upper and lower bounds on roots. So this is a further bounds sort of estimates on roots. Let P be a polynomial with real coefficients, and let the leading order coefficient be greater than 0. If P of X is synthetically divided by some C greater than 0, and each term in the result for synthetic division is non-negative, then C is an upper bound for the roots of the polynomial P. If P is synthetically divided by D less than 0, and each term in the result for synthetic division alternate in signs, where you can arbitrarily give a sign of a 0 coefficient, then D is a lower bound for the roots of P of X equaling 0. So let me do this. So I sort of got rid of that problem, and now I guess I'll do it. And it's on some page, and I have no idea what page it is. On page I'll say 519-ish. I'm guessing because I'm just looking, and that was one of the pages. Okay, so let's do this. So, I'll need much more room here to do this. Okay, so let's just sort of arbitrarily pick something that I think will probably work. Let's look at like -3 or something. Okay. So let's find some bounds. Determine integer bounds. Actually, maybe I'll do the largest one. So either 3 or 4 should work. So let's just try 3. Let's see, that's a 1, 1, -8, -8, 15, 15. Okay, so that's a 1 times 3 is 3, plus 1 is 4, 12, 4, 12, good. These are all, okay. 4, 12, 27, 60, 81, 96. Okay, so they're all positive. And so because of that, that implies that 3 is an upper bound. I don't know if 2 would have worked, but I tried 3 and 3 worked. So I just sort of guessed to see which one would work. I was hoping 3 would work. Okay, so now let's do -2, -3. -2 might work, but I'm going to try -2. That's really kind of, I would say that that's more than likely it's not going to work. So I'm going to try -2 with the feeling in my gut that -2 is not going to work. And so let's do 1 times -2 is -2. minus 1, plus 1 is minus 1. That gives me a plus 2. And then you get a minus 6. So it didn't work. So I tried minus 2, but this doesn't work because it's not alternating. So let's try like minus 3. 1, 1. Certainly 4 would work. Okay, so 1 minus 3 gives you a minus. Oh, wait. So let's try 4. So 3 doesn't work, but maybe 4 does. I don't want to give 2 that's incorrect. So let's do 4. Okay, so minus 4 gives you minus 3, which gives you a 12. Good, which is 4, which gives you a minus 16, which is gigantic, minus 24. This gives you 96. Again, gigantic. This gives you 111, which gives you negative 444. Assuming they haven't done any arithmetic error here, but it should be pretty close. And so this is going to give you a negative 425.29. So it alternates in sign. So that gives you a lower bound. So negative 4 is a lower bound. So you know that if you're going to be trying, you should pick numbers between negative 4 and positive 3, because you know that numbers bigger than 3 or less than negative 4 will not work. Okay, so this gives you just a rough idea of at least home in to values to check coefficients. Let the leading order coefficient of your polynomial just be 1, so it's a monic polynomial, and let the degree of your polynomial be greater than 0, so it's a non-constant polynomial, and let m be the largest of the coefficients except for the leading order coefficients. Then all the real roots of p, your polynomial, lie in the closed interval from negative m plus 1 to positive m plus 1, where m is the largest of the absolute values of the coefficients of your polynomial, except for that leading order coefficient. Okay, so let's do an example. Determine the Cauchy bound for the real roots of the following polynomial. 3x to the 6 minus 4x to the 5th minus 21x to the 4th plus 4x to the 3rd plus 8x squared plus 8x plus 32. So let's find the maximum. So let's find the Cauchy bound for this. And so let's find the largest. Okay, 1 second. Let's just turn off that. Oh, I guess it's off. Okay. Okay, it's off now. Let's turn off. And so let's find the maximum of the values oops, of the values. I guess defining the Cauchy bound. First, let's rewrite this so that it's a monic polynomial. And so let's write this as x to the 6th minus 4/3 x to the 5th minus 7 x to the 4 plus 4/3 x to the 3rd plus 8/3 x squared plus 8/3 x plus 32/3. Equals 0. Okay, so let's rewrite it so that this is a monic polynomial. Just divide every coefficient by the leading order coefficient, 1. So now let's find the maximum of the coefficients, and let's take the absolute value of each of them. So 4/3, 7, 4/3, 8/3, 8/3, and 32/3. So the largest of those, and I guess I'm going to be calling this M. Okay, let's try this. So I'll call this M. And so the largest of these is just 32/3. Therefore, the real roots, so by Cauchy's bound, all real roots of my polynomial lie between -2/3, so it'll be a 35/3, to positive 35/3. And that is the Cauchy bound for my polynomial. Okay, good. Let me do Roche's bound, or Roche's bound. And so let P be a polynomial, in this case, with complex coefficients. Let the leading order coefficient of the polynomial be 1, so it's a monopolynomial. Let the degree of the polynomial be greater than 0, and so that means that this is a non-constant polynomial. Let M be the minimum of these 4 values, 1 plus the maximum of the absolute value of these coefficients, except for the leading order coefficient. The same bound that we had, this is just the M from above, so the 1 plus M here. 1 plus the sum of all these coefficients, except for the leading order coefficients. The maximum of 2 times the jth root of the absolute value of the coefficients for, well, all of them except for the leading order coefficient and the constant coefficient, and the absolute value of the constant coefficient. So the minimum of those values Then the magnitude of all the roots, including the complex roots. So this is in the complex plane. Lie in the closed interval minus m to positive m. Okay, so let's do next example. So I want to determine Roche's limit, Roche's bound for the following polynomial: x to the 5 plus x to the 4 minus 8x to the third minus 8x squared plus 15x plus 15. So let's find the bound on these roots for this equation. So first, let's look at, so it's the minimum of these four values. So let's figure out, so let's do Roche's limit. Determine. Well, each of these numbers in the Roche bound. So let's do that. So one of them was 1 plus the maximum for numbers for every coefficient except for the leading order coefficient. And so, and maybe I'll just sort of say this is 1 plus the maximum of these values. And so 1, 8, 8, 15, 15. So those are the coefficients here of the polynomial, of this monopolynomial. So let's figure out the largest of these. Well, the largest of these is 15. And so this is 16. Okay, good. Just like what we had in Cauchy's bound. Next, let's determine 1 plus the sum j equaling 0 to 5, 4, absolute value of a sub j.
I have a question.
Yes.
You wrote down the coefficients. How come they weren't negative for the 8?
Oh, it's absolute value.
Oh, okay, sorry.
Yeah. So these are absolute values.
How come there's only one?
Because you don't do the leading order coefficient.
Oh,
So
okay.
you don't do, this is less than 5, the way I wrote it. You don't do this one.
Okay.
You just throw out that one. Yeah, in this. Okay. So now let's do, so this would be 1 plus, well, let's add these all up. And so this is just going to be 1 plus 8 plus 8 plus 15 plus 15. Okay? It's gigantic. Actually, that's where they get this one here for the leading order coefficient in the calculation. Okay, so this is equal to 1048. That's a big number. Okay, next. Let's find the maximum of Oh, wait 1 second. Yes, it is written there correctly. So the maximum of from 1 to 4 of 2 to 5 minus j to the 1 over j. Oh, maybe I should write it this way as the jth root. Oh, I see. Maybe not, because if I plug in 1, the first one doesn't work. So 1 over j in absolute value. And a sub 0. Okay, so let's do this. So this is equal to the maximum of, so maybe I'll just write them down and then actually calculate them. So this is equal to the maximum of 2 a4 oh, come on. 2 a3. And maybe actually I will put the square root there. So now I'll put the square roots. 2 a2 2 a3 a1, sorry, and then a0. Okay, so let's find the maximum of those. So this is equal to the maximum of 2. And so a sub 4 is 1, so a sub is 8. A sub 2 is 8. A sub 1 is 15. And a sub 0 is 15. Okay. So this is the maximum of 2. Square root of 8 is 2 rad 2, so that's 4 rad 2. Still a relatively small number. Okay, the cube root of 8 is 2 times 2 is 4. And the fourth root of 15 is something small. And 15 is something big. And so the maximum of all those numbers is 15. Okay. So the minimum. So now I want to find the minimum of, I wonder if I should write it this way. So the minimum of the way it was written in the theorem, the maximum a sub j Oh, okay, sure. Okay. Oh, 2 rad. Not that it really matters, because, let's see if I can do it. 8 can be written as 4 times 2. And the square root of 4 is 2. And so if you have 2 rad 8, then 2 times 2 is 4. But not that it really matters. 15 is much bigger than 2 rad 8. So it doesn't really matter if I simplified it or not. Each of those values are much, much smaller than 15. Okay, so this is the minimum of what we calculated. 0 to 5. Oh, I see. Let's write that as 4. Yeah, I did write. Let me just check if I, oh, I see, I wrote it this way. It's the same thing, but maybe I should write it as a 4. Okay, so the first thing we calculated, comma, 1 plus the sum j equaling 0 to 4 a sub j. So it's just the things we added up. And then the last number we just did, the maximum, 1 to 4 of 2 a sub 4 of 5 minus j to the 1 over j and a sub 0. Okay, so let's figure out what that is. So this is the minimum of 1 plus, which we found to be 16. The sum, which was gigantic, 48. And this maximum of these numbers here, which I found to be 15. And so the minimum of all these is 15. And so this says that the magnitude, and so this is the complex, if you have a complex number, you can take its magnitude. So the magnitude of all these complex roots of every root including the complex roots. Line the interval. Minus 15 to plus 15. And that is your answer. So that finishes off section 5.2. Let's go on to section 5.3. So in this case, these bounds are pretty big. They don't really give you any useful information to actually solve the equation. So these give you some sort of say, well, it's in between these values, but you'll find that It's a lot of work for very little information. Sturm's theorem, the Sturm sequence, gave us more information, but it was still a lot of work.